Okay, I think I should start because today I will be taking a tutorial kind of lecture. First of all, I will introduce myself. So, I am Anjali Negi. I am currently pursuing PhD in IIT Kanpur as a physical chemist in the research field of theoretical and computational chemistry. So last time I got a feedback of teaching some topic. So the topic that I was requested was the improper axis of rotation as a symmetry element in group theory. Okay, so before moving to this improper axis of rotation particularly, I will go through each and every like introductory session of each and every symmetry element and discuss some example with each of them. So yes, I will start. So okay, so you are able to see my screen and audio is also clear, right? Yeah, Pranoy.
Yes, ma'am.
So my video is clear, right? The screen is shared and the audio is also clear.
Yes, ma'am.
Okay, yeah. So I can start. So as in last one, I discussed about the symmetry. So the symmetry word itself, if you can understand, the symmetry that you see around yourself, and so the question is that in a molecule or in particularly atoms, in structure like complexes, how you can be quantitative about it, like which one is having a more symmetry. Okay, which one is having more symmetry and all. Okay, so the symmetry element and symmetry operations are built up to define which molecule is particularly more symmetric with respect in comparison to the other one. Okay, so the symmetry element and symmetry operations that we study in group theory particularly, so this is, I will again introduce that this is a particularly introductory lecture in group theory. So you first, when you go to the point group section, which is a mathematical form of applying this symmetry element and operation, is actually the second part of this, when you get introduced with the elements and operation that you apply on particular molecules. Okay, so this is the introductory lecture I am taking for today. So yes, so the symmetry operation is a movement. Okay, so it is a movement which any object can go from one configuration to other configuration by some operation we are doing in that particular molecule, and such that we can get an equivalent or identical configuration. So by equivalent and identical, I hope that you understand that these two are very different, because in if I am tagging a particular say hydrogen atom in water molecule, okay, so that particular hydrogen atom which I have tagged, after some particular rotation around one axis, it that particular tagged hydrogen atom will not be in the position that it was before. So for me, if I am tagging the hydrogen atom, I can see that the other configuration that I am getting is actually different from the previous one. So it is not identical, but it is equivalent to it if I did some kind of operation which gave me some equivalent configuration. So there we get the difference between the equivalent and identical configuration. And I have discussed that this is the equilateral triangle, for example, where I have tagged 1, 2 and 3 to the side of each equilateral triangle. And after, so this axis, that the yellow one, is actually passing through the center. So this is above and below the plane it is going through the equilateral triangle, and so this is giving me a 120-degree rotation. Okay, so 120-degree rotation will move my 1 to the 3 position and my 3 to the second position, such that I will get some configuration which is indistinguishable with respect to the first one. And again, if I am doing this 120-degree rotation about that particular axis, I will get again a different configuration because I have tagged them. I can see, and this is again indistinguishable. When I am again rotating my triangle, then I will get the identical one because it is tagged as in the first one. Okay, so this is what we can understand by symmetry operation, because the particular gist is that we need to get the indistinguishable configuration at each point such that I can call that particular operation as symmetry operation. So these movement by which I can get indistinguishable structure or even identical structure, okay, they are called the symmetry operations. Now, what are symmetry elements? So when I am saying symmetry element, so this element is some entity within the body or outside the body, okay, of the molecule or any object. It can be an axis, it can be a point, it can be a plane. So when it is so this axis, plane and point about which symmetry operation take place, like in previous example, in triangular equilateral triangle, the entity about which the operation was taking place was axis, which was passing through the center of that particular equilateral triangle. Okay, so that what we call as symmetry element, and we get an indistinguishable structure. So our main gist is that we want to get the indistinguishable structure. So this will be known as the symmetry element. So for example, in previous example we have seen that it was a rotational axis which was the symmetry element. So if an object or molecule has more number of symmetry element, okay, this is very important, because if any molecule have more number of symmetry element, and so does if it has a more number of symmetry element, it will have a lot more number of symmetry operation. Then the object and molecule is more symmetric, okay, in comparison to any other. So for example, here I have water molecule, ammonia, and one benzene ring. So you can see that if you take this example for later stage also, when you will complete all the symmetry element, you can count what particular symmetry element is present in 1, 2 and 3 in these 3 different structure of molecules, and you can see which one is more symmetric in comparison to other. Okay, so now what different symmetry element and symmetry operation that a molecule can have is a question. Like, you have seen axis of rotation, but what are the other symmetry element that we can have that symmetry operation will take place, and I will get an indistinguishable structure which is symmetric. Okay, so one can have a total of 5 different symmetry elements, okay, that can generate several symmetry operations. So total there are only 5 symmetry elements that we see. So those are: number 1, identity; number 2, proper axis of rotation; number 3, mirror planes; number 4, center of symmetry; number 5, improper axis of rotation. So yes, for identity you can denote it as capital E, and you can keep in mind that identity means doing nothing. So it means, for example, you can take this water molecule here, and about this axis which is passing through oxygen atom and dividing this angle HOH and bisecting it. Okay, so this particular axis, if I am doing a rotation of 360 degree, it means that it is this H1 will come back to its position again after the rotation, and this particular rotation is giving me nothing but the identical configuration. Hence I am doing in a sense I am doing nothing. Okay, so this is what we call as identity symmetry element, and this particular symmetry element is actually present in every single molecule, correct? So now second is the proper axis of rotation. So this symmetry element I can move. So this symmetry element is the axis of rotation. Now the word proper here, you will in general when I was studying in my masters, I also used to ignore this word proper, and I just read it as a axis of rotation or the principal axis of rotation that we have, and particularly the principal axis of rotation is the one having the n, that is the order of operation having highest in value. Okay, so this I have to I kept in my mind. But when you are dealing with the fifth element, that is the improper axis of rotation, you will get to know that there is a proper axis of rotation and why it is called a proper and why it is called a improper one. Okay, so this symmetry element, the proper axis of rotation, is denoted as capital C. In suffix there is n, where n is the order of operation. By order of operation I mean, because it's a rotational axis, that is the operation should be rotation. Okay, and for example, if my n is equal to 2, my rotation will be 180 degree about that particular axis, that is C2. Okay, n equal to 3, then it will be 120 degree rotation, that will be C3. N equal to 4, that will be 90 degree of rotation about that axis, and that axis will be C4. And n equal to 6, that is the 60 degree rotation, and the axis will be C6. So in general, I can say that my n is equal to, I can demonstrate at 360 degree, that is the whole angle, divided by angle of rotation, that is what angle of rotation I am doing for about that axis. So if I am doing 120 degree rotation, it will be 360 divided by 180 degree, and I will get n equal to 2. That will be my order of operation. Correct? So the principal axis of rotation, that is Cn, is Cn. Okay, so for example, here it is a very simple object square. If I say, so this is 1 2 3 4, I tagged it as 1 2 3 4, and then if I'm, so this axis, this particular axis is passing through the center of the square, and this is above and this is below the plane. Just imagine that the square is lying on your table surface or on your sheet. Okay, and the axis is above and below, passing through the center. And this C4 will do, because it is a C4, it will do a 90 degree rotation. So this will give me, because it is doing a 90 degree rotation, my 1 will come here, okay, and my 2 will go here, 3 and 4. So this is what we do as a principal axis of rotation. Because I am getting an indistinguishable structure, this is a symmetry operation. Now you can calculate the n is equal to 360 degree by 90 degree. I will get n equal to 4, and this axis is known as C4. Okay, so this was just an example. Okay, there's a point to be noted that C1, because C1, so n is equal to 1, that means my n is 1, that means n is 360 by 360. Okay, so that is I am doing a rotation of 360 degree full, that is equal to identity E. Correct? So C1 is identity E. And what will be C infinite? So C infinite is something which you can demonstrate or understand by this particular molecule CO2. This is a linear molecule, and if I pass one axis like this in red in color, so this particular axis is the axis of rotation. If I take this as an axis of rotation and rotate my molecule, so I will have indistinguishable structure which are infinite in number, because at any angle I will get the indistinguishable structure. So this is why we have this C infinite axis here. Okay, now the molecule can have more than one type of axis of rotation. It's evident, it's clear that any molecule, if I see the rotational axis giving me a indistinguishable structure, I will have not only one but more than one. I can have axis of rotation or proper axis of rotation. So for example, this triangular planar molecule, so this molecule you can see here, for example BF3. Okay, so we have 1 2 and 3 atom here and one atom placed here. So this particular axis passing through the atom in the center, so this is C3 rotation. How? Because I am doing a rotation for about 120 degree, correct? So this is a C3 axis of rotation. I am getting a indistinguishable structure at each time, at each 120 degree rotation. And for C2, For C2, my axis will pass through two atoms simultaneously. So if this is fluorine, so it will pass through fluorine and then bromine, and this particular axis will be C2. Okay, how? Because I will do a 180-degree rotation such that this atom will flip here and this will go here. Okay, so there are two rotational axis present here, which is C3 and C2 in this particular molecule. And if I am counting upon the principal axis of rotation, it will be C3, as it has n of higher value. Here in BF3, so C3 and C2, they are not coinciding, but inside a molecule you can have more than one proper axis of symmetry coinciding together. Okay, so why I'm saying this? Because there are some molecule, for example benzene here, because these two axes C3 and C2 were not coinciding, but in benzene you can see that there are some axes which is C6, C2, C3. If you will draw, you will see that some of them coincide with each other. Okay, so you can do this, and you can find how many C6 we have, how many C2 and C3 we have in benzene molecule. So now going, so this is important. So this is another element, mirror planes. So mirror plane is denoted as sigma, and we say that all plane of symmetry are denoted by the symbol sigma. Now there can be different type of sigmas. Okay, so one is sigma h, one is sigma v, another one is sigma d. So sigma h, for h, just keep in mind h means horizontal, v means vertical, and d means dihedral. Okay, so h means horizontal. So there is mirror plane. Okay, this mirror plane perpendicular to a principal axis of rotation. So that means it is horizontal to my principal axis of rotation. So this mirror plane will be horizontal to my any axis of rotation, Cn. Okay, which is principal axis of rotation. Okay, now yes, so sigma v, which is vertical, so this mirror plane containing principal axis of rotation, so this will contain the principal axis of rotation. That means it is, so it will be this mirror plane contain that particular principal axis of rotation. Okay, and again as in definition you can see it is saying not only plane but mirror plane. So mirror planes means it will do reflection. What does mirror do? It does the reflection. So in definition itself you will get what the operation it will do. Okay, so yes, again sigma d is the mirror plane which bisect the dihedral angle made by the principal axis of rotation and the two adjacent C2 axes perpendicular to principal rotation axis. So this is a little bit you can understand. I have the example in later slide also, but here you can understand that this is a benzene molecule. So if say yeah, this is your C2. Okay, that is, I can flip the whole benzene ring in 180-degree rotation and I will get again a symmetry structure, and this is again another C2, correct? Yeah, and then the principal axis, which is C6 here, passing through the center above and below the plane of the benzene ring, and my dihed. So this, what does the sigma d says? Sigma d says that it is a mirror plane bisecting the dihedral angle. So dihedral angle made between this principal axis and this C2 and this C2. Okay, so there will be this angle, okay, which will be bisecting. So my plane becomes, so this is my plane. So this is my sigma d, okay, and you can see that this particular plane, when reflect my molecule, if you see that reflection of this point, and this point will be equivalent and will reflect something like here. So this will give me the benzene structure again, and this will be indistinguishable structure. So this is a symmetry operation. So sigma d here is doing a symmetry operation, and hence this plane is a symmetry element, which is sigma d. Okay, so I will just stop here and ask you if you have any doubt, because this sigma d is important if you can understand. So any doubt? Okay. So if you have understand the mirror planes and understand sigma h, sigma v, sigma d, then I will move. So till now, what you have understood, that the symmetry element and symmetry operation, okay, and any given movement of a body, okay, or any molecule that brings the body back to an indistinguishable structure, that is called a symmetry operation. And the symmetry operation are taking place about any point axis plane, correct, which may or may not be included in the body, correct. So these plane axis or point are known as a symmetry element, correct. We have seen symmetry element up to mirror planes. So this mirror plane have reflection of any given point, as I have shown you in the benzene molecule. These three points were reflecting and giving back the benzene structure itself, such that after reflection through the particular plane we will get an indistinguishable structure again, correct. So this was my mirror plane. So the plane after reflection find out equivalent on the other side of the plane. This plane is the plane of symmetry. Okay, you understand, I think you understand the concept of mirror planes and the symmetry element of mirror planes. Okay, so for example, so this is a molecule, okay, CHCl3. okay, so consider, imagine the structure, and then just imagine the particular mirror planes that are present in that this molecule CHCl3. So you will see, I will just draw one. So sigma v is the, so what is the principal axis here? Anyone in CHCl3?
C3, ma'am.
Correct. So this will be my principal axis of rotation. This is C3. Okay, and so there is no C2, correct, है ना? There is no C2 here, only C3 is present. And then okay, so sigma v was the plane which was containing principal axis of rotation, and also it also contained the principal axis of rotation, plus it also reflect the molecule in such a way that I will get an indistinguishable structure. So you have to keep that in mind. And then so the plane will be something like for example, this particular bond is behind my sheet, okay, and so if my plane is containing this hydrogen atom, this carbon, and this Cl, this plane, such that yes, so I will be having some plane like this. Wait, or I can just say ki these three atoms in one plane. So this plane that I can draw is so what 2 points are reflecting? The 2 points which are reflecting are this Cl and this Cl, okay, and this sigma v will be so 1 2 3, either these three atom in one plane, so that will be 1 sigma v, and another 1 2 3, so these 3 in 1, and 1 2 3, these 3 in 1, so total we will have 3 sigma v mirror planes present in this particular molecule. For sigma h, if I will say for sigma h, so is there any sigma h here? Because sigma h is the horizontal plane to this particular principal axis. So if I draw any horizontal plane in this particular with respect to this particular principal axis, then I will I have the reflection and get the indistinguishable structure for this molecule CHCl3?
No, ma'am.
Correct. So no. So therefore we have sigma h equal to 0 here. Again for benzene. So for benzene, as I have shown you in sigma d, so there was a sigma d present, correct, in benzene. So it was like this. So this was the plane which was reflecting the molecule and the point, and this was called as sigma d. It was dihedral. Why? Because these two red one are the C2 axis, okay, C2 axis, or this if I will say this is a plane also passing containing the principal axis C6 here, okay, so this will be sigma v, okay, so it is sigma v here, and this one is sigma d dihedral, and again there is a horizontal plane present in this, so which is cutting. For example, just imagine that it will cut the benzene planar ring into two halves, such that half of the molecule, half of the atom is above, and half of the atom is below the particular sigma h plane, okay. So here in benzene we have sigma v, sigma h, and sigma d, all the three mirror plane present. Now for this molecule PTCl4, you can do it by yourself and find out what are the sigmas mirror planes are present here, and okay, and just find out the principal axis. So the principal axis that will be present here will be
C4, ma'am.
correct. So this will be C4 passing through the center of metal PT, platinum, and this will be C4. C4, that means it will do a rotation of 90 degree, correct? So this will do the rotation of 90 degree. Now this particular principal axis which is passing through the center, this will have some plane. If I say this will be sigma v. Why? Because it will contain the principal axis and vertical to it, and this will reflect whole molecule again, and hence it is a sigma v. And so this is one sigma v. Another sigma v will be like something like this. Correct. And so sigma v is present here. Sigma h will be present, yes. And for sigma d, if I am talking about, so for sigma d, say with this particular 3 atom, one chlorine, metal, again chlorine, if there is C2, yes, there is a C2, because it will give me the configuration again after 180 degree rotation. So this C2, and this is again another C2. So for sigma d, my definition was this simple, that my plane has to bisect the angle between this principal axis, this C2 and this C2, two adjacent C2. So this is the angle, and if I draw one plane bisecting this, so if this is the plane, So yes, it is reflecting the molecule, and I will call this plane as sigma d. So you can say that the sigma d is bisect two dihedral angle formed from two adjacent sigma v. Also, yeah, formed from two adjacent C2, or you can say sigma v also. Okay. So this is whole. You can see that sigma v, sigma d, sigma h I have drawn here. Okay, so there are two sigma d present, two sigma v present, and one sigma h present. Okay, so what is our aim? Our aim is to classify molecule in terms of symmetries and quantify which one is more symmetric using number of symmetry element and operations. So sigma v, again, for so you have seen that there are two sigma v, this one and this one, but these two are not very different. Okay, but in a water molecule, if you will take sigma v, so in water molecule it can do same operation, but they are actually different. So why I am saying it different? Because when you will go towards a character table and all, you will see that there you should know the difference between these two sigma v planes, and these two sigma v planes I can define it as like one sigma v prime and another one is sigma v simply. So in water molecule, how they are different? So you can just see the difference by tagging one hydrogen atom. So so this, look at this structure. So this is the hydrogen atom tagged as star asterisk here. So if, and this is the rotational axis, which is C2 present here. Okay, this is C2, and if I am doing reflection, that is sigma v here, okay, containing this axis. So this sigma v will do the reflection and I will get the structure as here. So this is my tagged hydrogen, which is now here. For another sigma v, so again this is the principal axis, this is my sigma v containing 1, 2, 3 atom in the plane. Here it was only oxygen atom in the plane, here I have all the 3 atom in the plane. So this will do again reflection such that there is no change in the position of my H asterisk. So that is why this sigma v is prime is different from this sigma v. So just giving you insight about like how you should keep in mind. Okay, now this is the fourth symmetry element, which is again important because this is center of symmetry. So when I am saying center of symmetry, it is also known as center of inversion and denoted as small I. And for any given structure or molecule structure, if you can produce equivalent point by passing or taking point on the object and passing through a particular point and getting the equivalent point on the other side. So this is a little bit confusing. I will just make you understand through this example. So take this point A, okay, and this has some Cartesian coordinate as x, y and z. And again there is another point A prime such that its Cartesian coordinate is equal but in negative amplitude. So it is minus x, minus y, minus z. Okay, now there should be one point in between these two A and A prime such that this is known as the red one, I. And how? Because if I go in equal direction from this particular point, here I will have a reflection of this in the equal distance, which is A. Okay, so going equal distance from I will get the center of symmetry. Okay, so this is the center of symmetry, which is denoted as I. For example, in benzene you can find the center of symmetry easily. So in benzene molecule, so this was the center. Okay, and how this is the center of symmetry I? Because if I move towards here, so I will find one what is here, carbon atom, and say this is hydrogen atom. Even the hydrogen and carbon, both of them get reflected and are in equal distance, and that is why this particular point is center of symmetry I. And not only this, but whole of the molecule I can go from this particular point and I will have the same point reflecting in a equal distance, and that is why we call it as a center of symmetry. Now so again, this ethylene molecule, this molecule you will have the center of, so this is the ethylene molecule. So if you draw this particular structure, you will see that this hydrogen atom, so this hydrogen atom will get reflected from with respect to this particular point in this direction, and you will have the same hydrogen, I mean the structure will be indistinguishable. Okay, so this is the point which we will call as center of symmetry in this ethylene molecule. Okay, now the octahedral molecule. So in octahedral molecule, what we had in any complex, we had 6 different coordinated ligands, or not, if I say all this 1 2 3 4 5 6 are equal, and at the center, so this is the center. If I will be moving, say I am doing the center of symmetry operation, so what does this center of symmetry operation does? It reflects all the point. For example, 1, it will reflect here, and this 6 will reflected here. So basically this center of symmetry or center of inversion is doing the inversion of the structure. So this structure will get inverted such that this 3 will be here, this 5 will be here, because this 3 get reflected here and this 5 get reflected here. Again this 4 will be reflected there, and that 2 will reflected here, such that this structure is actually the inverted structure of this one. Correct? So this is what my center of symmetry or center of inversion does. Now, so in CHCl3, do I have the center of inversion there? It's a question. In CHCl3, so you have seen the structure in CHCl3. It is a tetrahedral structure. Hydrogen, if you say at top, Cl bond at bottom. So can you imagine that it has a center of symmetry? Yeah, Narmada.
There is no center of symmetry, ma'am.
Yes, correct. So there is no center of symmetry in CHCl3. So it is actually you can see that it is not necessarily important that any molecule will have the center of symmetry. It can have other symmetry elements, but it is not necessary that, because identity is the one which every molecule has. Okay, but center of symmetry, we can see that in CHCl3 it is not present, but there are other symmetry elements which are present in CHCl3. Okay. Okay, so center of inversion, it inverts the structure. That what we should keep in mind. Again, this is a nice problem that you can do. Is this I, which is center of symmetry, versus C2, are both of them similar, or they are same? I mean, you can do this inversion I, and you can do C2 in a same molecule, and then see whether they will be similar, or they are same, or they are very different, or totally different. So what do you think? Any comment? Any quick comment? You can just comment, imagine any structure and see the operation that I and C2 does they give me the same structure? They are doing the same kind of operation? I'm asking this because I have asked you that C1 is actually identical to identity element because it was doing nothing. And C, what I was told that C2 is I. Yeah. So Gunasili,
Yes, ma'am.
so what do you think?
I mean, H2O, the C2 operation is different from I.
In H2O molecule, so C2, okay, and actually in H2O, is there I? Center of inversion?
Yes, ma'am.
Center of inversion is H2O. Wait. So this is my H2O. So you are saying that okay, this will be my C2, and so after C2 it will be a 180-degree rotation, and I will get, okay, so this will be my another configuration or structure. But center of inversion in H2O molecule, where it will be? I don't think so it has the center of inversion. Gunasila, you said it will have, so where it will be?
I mean, opposite side is the atom is present, but
Wait. No, H2O will not have this center of inversion because in inversion, because it is a point about which it will reflect the same structure, correct? So in H2O, can you find any point which will reflect? For example, let's say I keep one point here, okay, at this particular atom, oxygen, and so this point should reflect another so this atom will be reflected at equal distance and it will be somewhere here, okay, correct, but there is no hydrogen there, hydrogen is here, correct, so this point is not valid if I keep it on oxygen. And if I am not keeping it on oxygen, where if I'm keeping the point here, okay, and say I'm keeping the point here, inversion point, so okay, so this just assume that this point is here, and so such that these two hydrogen are getting reflected at equal distance, correct, that will be fine. But what about this oxygen? This oxygen will not get reflected because here is no oxygen present, so this is again false, so this point will not be called as the center of inversion, correct?
yes, ma'am.
So in H2O molecule, as in CHCl3, so in CHCl3 you itself said that there will be no center of inversion. You said it. Why you said it? Because if you keep any say take this carbon as the center of inversion, this hydrogen is not reflected back here because there is no hydrogen present there. So if I am taking this as center of inversion, this every atom should get reflected to the same atom. So for example, for this one, no, if I am saying this 1 and 6 are actually hydrogen and oxygen, for example, so this will be no center of inversion. But if it is hydrogen hydrogen, then this 1 and 6 can do reflection around this particular point, and hence it will be a center of inversion. But the condition was that this 4 and 2 should be equal, this 5 and 3 should be equal. Similarly, in ethylene, this hydrogen were getting reflected around this particular point. That is why it was the center of inversion. Again, this was getting reflected, and this carbon was getting reflected about the same say connected axis and same distance. Okay, but in water molecule, you will see that this water molecule, this oxygen doesn't have any other counterpart or counter atom at equal distance to itself, and hence we cannot have a center of inversion in H2O molecule, correct? So
Yes, ma'am.
yeah, so I should move. So this I and C2 that I have talked about are actually very different. I will I will just give you one example when I will finish this part, okay? So yeah, first I should finish this part. So the last symmetry element is left with the improper axis of rotation. So this improper axis of rotation is actually denoted as Sn. And this Sn, you can say that the rotation is, first of all, it is a combination of two different operations. So this is the very first element that you will see that is actually doing two different operations. So this is doing two different operations, and this is the only element which is doing the two different operations at the same time. So first it does rotation and then it does reflection. Okay, so the rotation about any axis followed by inversion through center of symmetry, or there is a plane present which will do the reflection. So taking any molecule, first of all, you have any molecule you have to find an axis which may or may not be the principal axis. Okay, mind this point, because this particular axis that you are doing the rotation first, it is not necessarily it is not necessarily that it will be the proper axis of rotation or principal axis of rotation that you have seen earlier. Okay, so it is not necessarily that it will do properly the inversion or you will get the indistinguishable structure at the first operation that you are doing. Okay, so you are just doing simply one rotation, so it will be known as the any rotational axis, but not necessarily the proper axis of rotation. But you find certain axis about which you can have certain degree of rotation followed by, now it is important, first you have done the rotation. Now it is not necessarily that you will get any indistinguishable structure, but after the rotation you will do the reflection on a plane which is perpendicular to the previous axis of rotation. Now the plane that you are doing the reflection should be perpendicular to the axis that you have done the rotation. Okay, now you end up with the indistinguishable structure. Now this finally you will end up with the indistinguishable structure. Okay, so this axis that we choose will be called as improper axis of rotation. Okay, first I will give you one example and I will try to explain through that, and after that I will ask you again if you have any doubt. So just hold on. So why it is called improper? Because it does not necessarily coincide with the proper axis of rotation. So mind it, because in proper axis of rotation there was a rotation which was just giving me the indistinguishable structure of the molecule itself, and we were done there. Okay, but here when we are doing this symmetry element which is known as improper axis of rotation, here we are doing two combination of operation, where first I will do the rotation, second I will do reflection, and this reflection will be through plane which is perpendicular to this rotational axis, and this rotational axis is obviously not the proper axis of rotation, because only after doing these two steps we will get the indistinguishable structure after that. Okay, not only by the rotation. So this Sn can be this Sn will be denoted as equal to Cn and then sigma perpendicular. Also in many books, or you will see that some will say that this is sigma h. However, this sigma h notation was used when it was the mirror plane doing reflection, when it was perpendicular with respect to what? Proper axis of rotation. Now here, since we are not taking the axis of rotation as proper, because it is not giving me indistinguishable structure itself, but we are taking any axis which is doing a little bit of rotation, and then we are doing the reflection. So hence I cannot use sigma h notation here. I have made a point here also that sigma perpendicular is actually not equal to sigma h, because sigma h is defined with respect to the proper axis of rotation there, in if you go back in the video. So n here is again order of rotation, as we have defined in C2C in the proper axis of rotation, where my n was 360 degree divided by the rotation we have done. Okay, now take this molecule, that is the tetrahedral molecule. So this is the tetrahedral molecule that I have. It is very important because I have made these two atoms as black, just to give you insight of where these atoms are moving after each operation I am doing. Okay, and these two as white. Okay, so if this is the axis passing through this particular center of this atom and bisecting the angle between these black atoms, so this will be the axis. Say I am doing the rotation 90 degree. So if I am doing the operation 90 degree, my n will be equal to 4. Okay, so I have done the rotation. So imagine the rotation is done by 90 degrees. So these two will be moved here, and these two which were okay, I will just, if say this is a plane. Okay, so if this yellow one is the plane of the paper, so say this atom and this atom are on this yellow plane. Okay, and after 90 degree rotation, which three atom will be on the plane? These two black one, and this atom will be on the plane of yellow. But these two which were on the plane of yellow plane, because yellow plane is not at all rotated, so these two white one will move away from that plane of yellow plane, and these will come here. Okay, so the rotational axis will be here. So what I have done only the 90 degree rotation. Now this particular configuration, ask yourself, this particular configuration, is it indistinguishable with respect to this one? It's a yes or no. So this configuration, is it indistinguishable with respect to this, or you can see that these two configuration are different?
Same configuration, ma'am?
No. See, the structure itself is very different. See, I don't know why you are saying same, but where you have the confusion, because these two atoms first they were in the plane of yellow plane, but after rotation this will move here, correct? Here this will go behind the plane.
4 atoms are same or different?
What? Sorry?
That 4 atoms are same or different, ma'am?
Okay, just imagine they are same. Even if they are same, the configuration will be different, because let's say I will 1 2 3 4. Okay, so even if they are same, the configuration is different because okay, just think about it, because this I have denoted this as black one and this as black one. Why? Because I wanted to give you the rotational insight, because I am not using any model, I am doing it in two-dimensional paper sheet, correct? So what I did a 90-degree rotation. So after rotation, this one is coming above your paper sheet. This 2 is imagine it is going inside your paper sheet or behind your paper sheet. Okay, and this 3 4 and this atom will be on your paper plane. Now rotate it 90-degree. What will happen? This 1 and 2 will come on your paper sheet, but this 3 and 4, this 3 will go behind your paper sheet, 4 will come above your paper sheet. Now what you are actually observing, you are observing that previously this particular atom was on the plane, again it is on the plane, but the above atoms which were outside the plane of the paper sheet now has come on the paper sheet, and the atoms which were below this particular atom were on the plane of the paper sheet now has gone outside the plane of the paper sheet. So what you have observed, you have observed a configuration which is different from the previous one. Is it clear?
Yes, ma'am. Clear, ma'am. Yes.
So see, imagine, so this configuration which is outside your paper sheet, above and below, and this is on your paper sheet, is very different in comparison to here, because here they are on the plane, but here they are outside the plane of your paper sheet. So now when you have done the 90-degree rotation, you can actually say that I have done the 90-degree rotation. That is why you can, because see, imagine this molecule was left on your desk, okay, or your paper sheet as you are imagining it right now, but after you have gone for 5-minute break and then came back, then you see that the okay, this 1 and 2 were outside the plane of the paper sheet, now they are on the plane of the paper sheet. Will you be able to observe the rotation? Will you say that it is being getting it got disturbed by someone, or someone rotated it? You will say, correct? You will be able to observe it. So when you are able to observe the rotation, and when you are able to distinguish that earlier when I took the break, it was not like this. When I came back, the configuration is disturbed. My 1 and 2 were outside the paper plane, now they are on the paper plane. So that is why this configuration are actually different. So hence this rotation that I have done, the 90-degree rotation, is actually not the symmetry operation. So what you have to do after this rotation, according to the definition, you have to find out one plane which is perpendicular to this rotational axis. So the plane which is perpendicular to, yeah, I know it's time, but I can just finish it. Okay, so this particular rotational axis will have a plane. So this is the plane. Okay, so this plane will be perpendicular to the axis, and now this will do the reflection. So Gunasli, this is very important. So this, when it is doing the reflection, I am getting back the configuration. So these two atoms which are now after rotation outside the plane, correct, they will get reflected something like this, which are here, and these which are on the plane will get reflected here. So this was the plane that was reflecting, and this will remain here. Is it clear to you? Now this configuration and this particular first configuration, so if you have taken the break and someone did the rotation and did the reflection of the plane, you came back after the break, but now will you be able to determine that someone disturbed your configuration? No, correct? So you will have the same configuration after the reflection as you had earlier before even doing the operation. So that is why this combination of rotation and reflection is known as the symmetry operation, because that what we want. Okay, so this S1 S2 are again two improper rotations, and yes, so this is a molecule, say H2O. Okay, just imagine it is a H2O molecule, sorry. So this will be I have just colored this one as black, or I can just simply tagged it, but I colored it in black. So this black one, after the rotation of S1, so S1, this is S1 is what? N is equal to 1 means it is doing a full rotation, that is 360 degree. That means it is doing actually nothing. So rotation of 360 degree, this will rotate and come back here, this will rotate and come back here. So this will be my configuration. So rotation is done. When I will do reflection, so this reflecting plane will be perpendicular plane with respect to this particular axis. So this is perpendicular to this axis. This will do the reflection. Now this reflection is done such that this tagged atom will go here. This atom which was not tagged will come down, but it is again on the plane. It is again on the plane. Now as this one and this one are H and H, and this was oxygen, H2O molecule. Again, Gunasli, if you took the break and someone did the rotation of 360 degree of your water molecule, which was water molecule model, which you kept on your table, and then they did the reflection again, so you will see that it is you cannot define that it is whether got disturbed, whether this configuration was different. So so this combination again is known as S1. So this S1 you can write it as C1 sigma perpendicular, and this C1 you can say that this was actually in C1 you did nothing, so it is actually equal to identity, and this S1 is nothing but operation by plane of symmetry. So you can actually skip the part of rotating the molecule and just do the reflection only, and then again you will say that S1 is actually nothing but the plane of symmetry, correct? Now for S2 molecule, so imagine this is again, say this is some atom, say HH, and this is some another atom, yes, CO2. Say this is oxygen, and this is carbon. So if I am doing S2 means I am doing C2 operation. So this is the axis which will do. Okay, Narmada, if you want to join that class, you can leave. Okay, so I actually I will just conclude this S2 operation. You can just give it a go and just define whether what operation we are doing. Okay, so let's conclude this class. I hope you understood the improper axis of rotation. If you guys have any doubt, you can write it down on the chat box. Okay, and Gunasli?
Ma'am, no doubt, ma'am.
Okay. Yeah, you can work out whether the I and C2 are actually giving me the similar configuration or different one. And you can tell me in the next class. Yeah, thank you.
Okay, ma'am. Thank you.